although we don't have the projector, is the discussion of the quantum mechanics related with hydrogenic atom of the hydrogen like those one electron system. It can be a hydrogen atom or ion that only have one electron. And we say, if you consider a system like this, then you're looking at two particles. The system consists of two particles, the nucleus and the electrons. So if you really want to consider this as a whole entity, then the Hamiltonian operator will consist the kinetic energy component for the nucleus plus the kinetic energy for the electron. And then you add the potential energy for the system. And we went through all of this, but you are solving for this particular system 6 variables. And we consider the nucleus is so much heavier than your electrons. We can approximate the nucleus stationary. So you can just do approximation, reduce the system from this two-particle event into only consider the Hamiltonian operator or the system as the electron movement with the nucleus as stationary. So this is not the Hamiltonian operator we will consider. Instead, we went through the whole justification reasoning that, okay, it is good approximation. So we only consider the system in the relative motion of the electrons to the nucleus. All right, so I think that's where we ended in previous lecture. So instead, now we consider the nucleus, all right, at the origin of your Cartesian coordinates, and then you're thinking about the electron. Okay, you might just refer to the electron as a, maybe I just, let me just do this. All right, you can consider the motion of the electron with respect to the nucleus. Then that will simplify. Why is that? Now you can think about it. I only have one coordinate that is the coordinate for that electron. So you reduce from 6 variables to a 3-variable system. Okay, now in that case, if that is our system, so you consider the relative motion to the nucleus. All right, if that is our consideration, then our Hamiltonian operator we only consider with one position coordinator that is really referred to the electron, right? And then you need to have the kinetic energy component, then you will have the potential energy component. Okay, now when you have a position coordinator, you can do it in the Cartesian or you can do it in the spherical. So basically, this position is referred to the electron. We can use X, Y, Z to refer the position for the electron, or we can use the R, theta, phi. All right, now it's easier for us to do it in the R, theta, phi. And furthermore, when we can consider the motion for the electron, we will going to borrow what we already learned. How we're going to do that is you can consider this electron motion. Okay, borrow it from you can consider this motion as the electron as a particle rotation on the sphere. Now, if this is the system, then the motion for the electron on the sphere is a fixed radius, but that's not the case. So what we're going to do is then plus vary the radius. So basically, we can think the wave function for the electron motion in the hydrogen-like system as they are particle in the the rotation, free particle rotation on the sphere. Now we introduce the variation for the radius. Now, if that is successful, if that is, that's what we're thinking, right? Now, if that is successful, then the wave function for that electron in, we can use R theta phi for the position. Then, if that is successful, then this can be, the wave function can be separated into the product that related with the solution for the particle rotation on the sphere, and then you will introduce additional function to reflect the true nature of the electron rotation on the hydrogen that has the variation of the radius. And that's what we're going to attack. Are you guys holding okay? That makes sense? Alrighty, okay. Alright, now, how are we going to do this? Alright, now, let's see. Can you guys come up the Hamiltonian operator for that electron in the system? So, when we consider electron motion only, and then we only have one position coordinator, then we'll have a wave function which carries 3 variables. How are we going to solve for it? We can solve by separation of the variables if we can know the electron orbits around the nucleus. Then we can borrow, we want to see if that works using particle rotation on the sphere, and only related with the angle component. And then that model has a fixed radius, but for the system electron in the hydrogen atom, the distance for the electron varies, orbit around the nucleus with variable radius, and we're going to bring that in. If that is successful, then the wave function for the electron can depend on the 2 components, what we call the angular component, and one we're going to call the radial component. Now, what exactly that would it be? We have to solve for it, but that's what our attempt for the strategy. Okay. All right. So once the strategy attempt for the strategy is clear, now let's try out. All right. So this is our exact Hamiltonian operator. Depends on one position coordinator. Right. So then this also, if I want to write out, is R theta phi. All right. What is the range for R? There's 3 variables. What is the range for R? 0 to infinity, right? Now how about the pi variable?
0 to 2 pi.
0 to 2 pi, just one, and then the theta.
0 to pi.
Very good, 0 to pi. Excellent. Okay, now let's do this. All right, so you have 2 component, kinetic energy component, and then you have the potential energy component. Now we say it's a motion of the electron with respect to the nucleus. All right, now, what do you think about the kinetic energy term? Operator.
Jeez, it's going to be h bar over 2m.
What is the kinetic energy operator?
Isn't it h bar over
The
2m?
kinetic energy operator always the same, right? What is it? It's the
Negative
you have a
I'm seeing a
constant,
negative, folks.
and then you have the second order derivative with respect to the motions in the axis that we're considering. Now, how many axes are we considering right now? I'm gonna call name. Actually, not how it has to be with the LSC. I want to know more. I mean, it's okay if you don't answer, but I want to know you guys. don't worry, I don't write the grades on the front page, so calling nothing to do. Because, now this is a side story. When I was going through from kindergarten to graduate school, I cared so much about grades. Actually, that's not true. When I go from kindergarten to the first year of graduate school, I cared so much about grades. I even cry in high school if I don't get the grades I want. So it's just like, because I want to get the best grades I want. If I don't get 100 or something.
And then you have the second derivative of.
You have a second order derivative with respect to all the axes, right? Yeah, that is great. And the electron moves along the three-dimensional space, so we have all those axes, right? Okay, now. I think
It's written as del.
Is that the same thing as del squared? The x1?
Yes, okay, so let's see. Aiden. You
Yes.
have Aiden? Oh, yeah, go ahead. What do you think about, will this equal to the del squared?
Yeah.
This whole thing equal to del squared? Okay, great. So we can potential funny. Alrighty. William, do you have a will?
That is.
Yeah, so I see Zach, you raise your hand, and I'm like, okay, this is all right, huh? Okay, how about the potential energy?
Potential energy.
What about the potential energy? Jacob,
That's the
what do you think? The potential energy for this,
We have to do Coulomb's law for that.
is that,
Potential.
do we agree there's a Coulomb potential?
Yes.
Very good. So what is the expression for the Coulomb potential?
It's like Q1 times Q2.
So let's just say I'm hydrogen-like. I'm just saying, let's just do it for the sake of the simplicity, just hydrogen atom. So what would be the potential? It will be the E squared versus 4 pi epsilon 0 and R, right? What is the R? R is the radius. With this, it's a vector, but you have a 3 variable R, 8 and 5. So the R is your variable distance from the origin for that 2 charge points, nucleus and electron. So that is your R right here. Isn't that your potential? Now, I think where you mentioned, what about the mass here, right? What about the mass here? So our system, you're looking at the relative motion for the electron in the nucleus. If we consider those two as a whole entity, what we can use is a nu, which is, gosh, I wish you guys would have more discussing your physics or math, because every time I introduce something, I just worry that you didn't get that training. If you have a 2-point system, we can have an effective mass or the reduced mass. Do you guys come across? Okay, now how do we calculate the reduced mass? This 1 over this, that equals to 1 over the mass 1 plus 1 over the mass 2. That's how we can calculate the reduced mass. Now for the 2-point mass, the reduced mass is the same way as the effective mass. All right, now for us, what do we have? We have one is for your nucleus and one for the electron. All right, now if you use the reduced mass, consider the whole thing as an entity. Because the mass for the electron is so much smaller, or one of the mass is so much smaller than the other, so you can be approximated. You guys can go home and do this math. The reduced mass for the system, it equals to the mass of the electron. So therefore, if you really want to make your life easy, I do not mind. You can just use the mass of the electron. Now, in this class, as you guys see, I want to emphasize what is the problem, why are we doing this, how we get there. Now, the specific detail of the mass and derivative, I leave it to you guys at home, because this is really a quantum mechanics course to let you introduce the principle and explain why we're doing this. All right, are we all following okay? So in the textbook, you may see the reduced mass, sure you can calculate that. But I'm okay with just approximated. I think the textbook will be okay, and your result will show you to be okay, because the differences is very, very small. You don't need to do that lengthy, detailed calculation. So therefore, the first term related with the Hamiltonian operator regarding the kinetic energy motion for the electron with respect to the nucleus, motion in three-dimensional axes, and then you have the potential energy. You know what I do next time is that I'll bring a chocolate if somebody identifies if I have anything on the board that is not right. Did you see there's something not quite right there?
You need the negative sign?
Okay, I can give 2 or 3. I'll be broken. We make some money as a sponsor, but not that rich. What is it? But I will do it next time. If I wrote something, the first one raising a hand, I'll definitely bring a chocolate. What is it? It's this, right? It should be a negative sign. Sorry about that. You guys should have changed that. Okay, all right. Now, we said we do not like to use it in the Cartesian coordinates. It's better for us, particularly if we want to use this model. We want to try separate for the rotation of the sphere and then introduce this radial component, whether this would work or not. So therefore, we would like to put it into the spherical coordinates for this 3 different components. Now, what do we have, guys? We show this expression when we're talking about the particle rotation on the sphere. Okay, this is really nothing fancy. It's just a conversion between x, y, z to now where's the theta phi, guys? Did you see the theta phi operation? It's a conversion between the Cartesian coordinate x, y, z to theta phi. Here's our second order, first order. Now the theta and the phi operation is contained in this operator. What do we call that? Legendre operator. Okay, do you guys still remember what this Legendre operator is? Okay, all right. Okay, you guys? Is the operation regarding with the theta and the phi component. So, any questions on that? Okay, if there's no questions, so this is our Hamiltonian operator. Now what we're going to do is we first have the model, and then we have a Hamiltonian operator. Then what we're going to do is straightforward. You will have this Hamiltonian operator operate onto the wave function and then plug into your Schrodinger equation to solve for the Schrodinger equation. That's how we're going to get the solution for the wave function. Once we know the solution for the wave function back into the Schrodinger equation, we will get the solution for the energy. That's a general scope we have been talking about. Now, when you're solving for it, look, guys, here is your Hamiltonian operator. You can plug into your Schrodinger equation, solving for this 3-variable function. What do? In math, sometimes we do tricks. What trick do we do? Separation of what?
Variables.
Instead of solving the exact one, sometimes it's so complicated, so therefore you learn this. I think you guys learned this in math. Instead of solving for the theta with 3 variables directly, one math trick you guys learn is separation of variables. Now you can't just say, okay, Dr. So told me that there's this separation variable, so any function that I have, I just boom, 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 separate into whatever it is. That's really not true. It has to have a reasonable judge to see it's an attempt of a separation of variable. Sometimes it did not work, and you have to, no choice, you have to go back and solve it in the exact. But here we have a reasonable basis by borrowing the particle rotation law. Because look how electron, it orbits motion in 3-dimensional space. So we could attempt as a particle motion on the sphere, then with no changing with the radius. So therefore we can have a function in the angular component. That function only depends on 2 variables. Then we will have a function introducing to add the variation of the radius. So in that regard, there's a reasonable attempt for us to try instead of directly solving for this. Now what can we do? We can attempt solving for, and then we will have another function that depends on the radius. All right, so your wave function can be a product of the 2 components. And then you solve for those 2. Instead of one depends on 2 variables, the other one depends on one of the variables. Any questions on this one? Okay, all right. Now, let's give it a shot. If this is the case, all right, this is our Schrodinger equation. If this is the case, then we have a Hamiltonian operator operate onto your wave function. Okay, I'm abbreviated it as a y function and r function. Y that equals to, that's your Hamiltonian operator operated onto the Ry, and that will equal to the energy of the Ry. Any questions on that? So this is your Schrodinger equation. Now what I did is just I plug in the Hamiltonian operator, operate onto the wave function. On the other side is your energy times the wave function. Ain't do anything fancy. Okay, alrighty. Now if the strategy is the separation of the variable, what should we do? You're solving for this mathematical equation for r and y here. R is the function related with the radius, and the y is related with the theta and phi. If you use the strategy of a separation variable, what should we do mathematically for the next step? Right, I don't think it's fair, I always get it from this pi, right? So let's see. Okay, Nicholas, that's the first one, right? Nicholas? Do you have Nicholas here? Okay. Jaden? Jaden? Yeah, what do you think? It's okay, just give it a shot. What do you think? Do you want Taylor to help you out?
Sure.
Okay. That's the rule, right? We want to separate. How do we want to separate, guys?
We're solving for one of the variables, like trying to get it wrong.
Yeah, so we try this in the particle rotation of the sphere, right? So spend some time. Okay, okay, I saw Grace. Grace, what do you think?
How to do separation?
Yeah, how do we separate with this problem we are having?
Oh, she was saying you just want to cancel out.
You want to have a. I feel so bad for you guys. Never exposed to something like this in your class. That's really not fun at all. Do you talk about in the math those separation variables? No. No, but we talked about briefly last time. So you're right. So what are we gonna do? Toward the end, we want to have the like. But after I teach you, you guys will know next time I ask. Okay, what do you want to have? Is it components with the variable here on the theta and phi. And then what else do you want to do? You want to have
Component that just has
components. I'm applying to this one. Only related with the other variable, and that equals to right. So you can separate those variables. Now, one thing we're thinking about, the function depends on the theta and phi, so therefore we group everything for that into the terms. And then we only have a component with a radius component. Okay, now how are we going, if I do that, how are we going to continuously continue? Think about it. If this component, so if I can separate it into this, then what that tells me is that I have something, add something to give a 0, which means if this cannot be variable anymore, this also cannot be what? Variable anymore. You guys agree? If it's a variable, add something, it would not be 0. So if I can separate into this, infer to me is this has to be a constant. This component also has to be constant. Because you add a variable, add something, it will give you a variable. All right, so that tells me further, this has to be a constant. This is also has to be a constant. All right, now let's keep it going. You have a constant, add another constant, they give it to you 0. What further constraint for us? Whatever this constant is, let's just say this equal to a constant A. This has to be negative constant A. All right, we are almost there. Give me goosebumps with how elegant the math can be. Now what do? Instead of one equation carries 3 variables, what we just successfully did is we actually split that equation into 2 equations, right? One is with the component, depends on specific variables, come up with one equation, and then you have a second equation right here. Then what you're going to solve is you're solving for this, give you a solution for one of the function, you're solving for this, give you a solution for the other function. So I'm just walk through with you with the idea how we're going to do a separation variable, and that's what we're going to do for our quantum mechanics. Now you have to evaluate yourself, right? So you have a second order derivative, first order derivative with R, you have a bunch of them with the theta, and then what are you going to do? You operate onto the function of the R and Y. So you're going to do all this math and operation, and then you're going to do the separation, and then split it into 2. And guess what I'm going to do, guys? I think I only have 10 minutes. I'm not going to go through all this splitting. How we're going to do that? I'll post that lecture notes, but you guys can enjoy that beauty. And that's how we got 2 functions. listed on the board right there. One is, after we do all of this, you separate it into that's one of your function. The y is your function here. Sorry, I'm taking a shortcut here. This side just wrote it in the y, this side just wrote it in the r. I didn't carry the y if I really want to write it out. Maybe I will. Just regarding with the data I and okay, and then I have other components that's related with the radius part. Okay, all right. So if you evaluate this, do the separation, you're going to split it into two parts, the angular component and the radial component. So for this particular equation, using the separation variable works, all right? Okay, now, if we take a look at this, so this is the h bar squared over 2, the mass, y, you have this operation equal constant. If you really look at this closely, this is really your solution. But if you don't believe me, go home and take a look at it. A particle is really the Hamiltonian Schrödinger equation for the particle rotation on the sphere. If that is the case, then the constant here, after we splitting, we take a look at it. This is really the Schrödinger equation for the particle rotation on the sphere. So if I take a look at, in that case, the constant equals to L plus 1, h bar squared over 2 mass of me. All right, I'm not gonna repeat on that one. So therefore, it is true for the electron motion in the hydrogen atom. If you monitor the electron, considering the rotation on the sphere model, and then plus the radial component. So therefore, parts of the solution for the electron in the hydrogen related with the angular component is exactly the solution for the particle rotation on the sphere. You guys follow me, okay? Which we already know. So in that case, we already know the wave function from the particle rotation on the sphere that we learned in chapter 7 math. All right. Now, here is the other part that allows us to solve for the wave function for the radius. Now what do we have here? We have h bar squared 2me times the radial component of the wave function r. Then you have all of this. All right. Then what else you have? What is the v here, guys? But what is the v here? Oh, and then I erased. What is the v in this equation?
Potential energy?
Yes, the V is the potential energy. V is the potential energy. Very good. So V equals to? I'm not going, I'm determined I'm not going to lose any chocolate on that time. So it's a negative. That's your potential energy. Is that right? And then what else do you have? You return the minus E. E is the, what is E here?
Energy.
Okay, all right. Now, how are we going to solve for this one? We want to make our life easy, as this slide indicates. This is the second component of the wave function, but instead, what we want to do, I feel bad for you guys, we're getting more and more complicated. What we would like to do is, instead of the solving for R directly, R is your radio component of the wave function, we will introduce another function as a substitution. It is the U, okay? UR. U is related with the R function, that is, we want to use a substitution. Instead of solving for this in math, if you use a substitution, they are linked together. The U function is just a manipulation of the R just equal to the U over R. The reason we are doing this is to, in math, when you're solving any particular equation, you need to introduce some tricks to make our life easy. And if you plug in this into this one, you manipulate it, and you guys can see that second component of the radio function in terms of the U has a very simplified expression. What do we have is you're going to become, if you do that substitution, then the radio component would be written like basically, in order to solve this one, it looks awfully abstract and complicated, but if we do the substitution, instead of solving for R right away with a U just equal to the R function times the variable R. If we do that, then this expression can be simplified. Guys, look at this. It's just in a function, second order with respect to the R variable. It's much easier to solve something like this. That's about it. Nothing fancy, but here we see the V effective. V effective is a group through the manipulation that equals to two components. One is your V, potential energy, and then plus so what I'm showing here up to this stage, it really has very little with quantum mechanics. Mostly is math. I said that math is important in this course, as you see here, because for quantum mechanics, all we're talking about, okay, I have this guy, how are you going to solve for it? And I just walk you through with the math components, and hopefully you guys can enjoy the beauty of the math a little bit. To solve for this one, we do not directly solving for the wave function with three variables. Instead, we separate into two of them, and how can we use separation variable and calculate the angular component and calculate the radial component. Now, for the radial component, we do not directly solving for the R. In turn, we're solving for the U. But once we know the U, then we will figure out the R, because R is just U function divided by the variable of R. Does that make sense? Okay, so Wednesday, we'll show the, finally we can show the wave function